You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So what's really exciting about making these weekly episodes is that we get to, in kind of real time, talk about the active scientific discoveries that are going on right now. And that's great because just a few weeks ago, we had a new discovery of gravitational waves from the collision of two black holes, the most massive collision that we've seen yet. This isn't the first gravitational wave detection, but it still teaches us some new things about physics. So today we want to give you all of the background and context that you need to really appreciate this discovery. So we'll talk about what gravitational waves are, why it's so hard to detect them, and we'll talk about what this recent detection teaches us about black holes. Just a quick note before we get started. Dan's mic was having some issues this week, so the audio from his end might be a little less crisp than usual. Hopefully that doesn't bother you too much. So all that being said, let's get started with the basics. What is a gravitational wave?
It's like the name implies, is a kind of a wave. In particular, it's a moving periodic variation in the curvature of space. So let's unpack that a little bit. So if you picture other kinds of waves, like say a water wave, that's a moving periodic variation, the height of a water's surface, or a sound wave. It's a moving pattern of alternating regions of high and low pressure. All waves are kind of a moving periodic variation in something. In the case of gravitational waves, it's actually the curvature or geometry of space itself.
So what this means is that as a gravitational wave passes through space, space is getting squashed and unsquashed. And this is a really weird thing.
In old Newtonian ideas of gravity, there was no such thing as a gravitational wave. Gravity was just something that was communicated instantly across space. They didn't really say how it worked. But in general relativity, gravitational waves are a necessary consequence of this theory. In particular, almost any kind of moving objects will create ripples or vibrations in the fabric of space and time. These rippling waves carry energy as they propagate through space, and they move through space at the speed of light.
So to understand why gravitational waves must exist according to relativity, but not according to classical physics, let's think of this scenario. Imagine that one day, the sun in the center of our solar system just disappeared instantaneously. So what does classical physics say should happen in this case? In classical physics, gravity is a force that acts at a distance onto objects. The Earth feels the force of gravity from the sun, described by Newton's equations, and so when the sun disappears, that force also instantaneously disappears. So immediately, the Earth will stop orbiting and just keep moving in whatever straight path it's facing in the moment that the sun disappears. That's for classical physics. But in general relativity, gravity is no longer this action at a distance type of force. Instead, it's the curving of space-time. So when the sun disappears, space-time will have to re-flatten right where the sun was. And so that'll create a ripple in space-time, just like dropping a pebble into a pond would. These ripples would take some time to reach Earth for the first time. It's actually approximately 8 minutes. So for about 8 minutes after the sun disappears, the Earth would actually stay in its orbit. So this example illustrates what is so different about classical physics versus general relativity, and hopefully gives you an idea of why general relativity necessitates gravitational waves while classical physics does not. But it doesn't actually take the sun disappearing mysteriously to create these gravitational waves.
So it turns out that just about any gravitating system will generate at least some gravitational waves. Even a system like a planet like the Earth in orbit around the sun will slowly emit gravitational waves into space. And as it does it, it loses energy, causing it to spiral closer to its host star. Now, it turns out in the case of the Earth, this is so slow that you'll never actually observe it. It's less than a trillionth of a meter per year that it gets closer to the sun. but we're pretty sure this is going on. General relativity says this should be going on at least this very small rate. So it turns out that there are some things in the universe that can make much larger and more intense forms of gravitational waves. These usually involve really massive and compact objects like black holes or neutron stars. So in particular, like a black hole is something that is so massive and so compact that even light can't escape. It's the ultimate kind of curvature of space. Neutron stars aren't quite as extreme, but they're still pretty extreme. A neutron star is essentially a sun's worth of mass squeezed into the volume of a city, but made up entirely of neutrons with very few protons or electrons or other sorts of matter. These things are so dense and so compact, so massive, that when two of these objects, black holes or neutron stars, merge into each other, they really screw up the surrounding curvature of space, and they create a huge amount of gravitational radiation or gravitational waves as they spiral into each other. So you could think of the Earth in spiraling towards the sun as kind of like dropping a little pebble into a pond or something. You make waves, but they're very mild, they're hard to detect. Whereas black holes or neutron stars undergoing mergers, it's more like a tsunami, enormous water waves that can destroy cities or wreak havoc on their surrounding environment.
So now we know what gravitational waves are, this essential side effect of general relativity. And even before we started detecting them directly, there was some solid, indirect evidence that these things were going to exist.
So by the 1960s or 70s, most experts in general relativity were pretty sure that gravitational waves would be real, but we didn't have any way to detect them. At least directly. But in 1974, we started to get the first, at least indirect evidence that gravitational waves were real. So this happened because some radio astronomers named Joe Taylor and Russell Hulse detected a pair of neutron stars in a close orbit to each other. So these are two neutron stars orbiting around each other in a very, very tight binary, rotating around each other in a very rapid fashion. We call this sort of thing a binary pulsar. So what a pulsar is one neutron star that's spinning very, very fast on its axis. So if you look at something like the sun will orbit around its axis once every month or so, whereas a typical pulsar spins around its axis about once a second. Some faster, some slower, but usually in that sort of ballpark. There's so much energy associated with that kinetic energy, that rotational kinetic energy, that these objects shoot out beams at the ends of their axes of radio and gamma rays, and we can detect these things. And because of the rotation, it turns out it leads to this really powerful pulsation signal that we can look for. Kind of picture something like a flashlight that shoots light out of both ends, and then starts spinning it around on its axis. Depending on where you are oriented relative to that flashlight, it might flash once or twice per revolution or per spin. And if you look at a pulsar out in space, you don't see all of its light being emitted, but every second or maybe half a second, it will shine in your direction and you'll see a clear signal. That's the telltale sign of a pulsar. So this object that Joe Taylor and Russell Hulse were observing in 1974 are two different pulsars in the same binary system. And we've never, at this point, had never observed anything like this before. And because they're so close to each other and the gravity was so strong, it provided a great opportunity to test general relativity in this strong curvature regime. So up to this point, we had only tested general relativity when gravity is pretty weak in things like the solar system and other sorts of systems like this. This provided an entirely new way to test general relativity. And over the years that followed these observations, it became clear that general relativity was making the right sort of predictions. The system that was being observed by Taylor and Hulse really did look and behave the way that Einstein's theory predicted it should. Also, at the same time, you could begin to measure the rate of change of the neutron star orbits in the system. After all, the gravitational waves from the system should carry away energy, and that should cause these pulsars to tighten in their orbits, getting closer and closer to each other, and gradually speeding up the rate of pulsations. This was over time, about a decade or so, confirmed at a rate of 76 millionths of a second a year. So it's incredibly precise, but it's the sort of thing a pulsar is enabled to do. And that's within a fraction of 1% of the predicted value from general relativity. So this provided the first real proof or evidence that gravitational waves really exist. These two pulsars, as they tightened their orbits and spun up, were emitting gravitational waves in large quantities into space all around them.
So now let's finally get to what it's like to detect gravitational waves directly. And this is no small task. The gravitational waves we are detecting come from black holes and other objects that are over 1 billion light years away sometimes. And by the time they reach us, these signals are tiny and shrouded in background noise.
Yeah, if you describe this sort of experiment to me and just said, we're going to try to do this, I'd say, like, wow, good luck. This just does not sound plausible. But here we are. The experimentalists are really good at their jobs.
Right now, the best technology for detecting gravitational waves is with a machine called a laser interferometer.
So here's how a laser interferometer works. You take a laser beam, you split it into two separate beams, which travel in different directions, and then are reversed by mirrors or something else and brought back together. If the two routes taken by these lasers are exactly the same length, then the peaks and troughs of their waves will fall on top of each other. And those peaks will just enhance the brightness, the troughs will be the darkest parts of the light, and you'll have basically a reinforced wave. We call this constructive interference. On the other hand, if one of those laser routes is a little bit longer by half of one wavelength than the other route, then the peak of one wave will fall in the trough of another wave and vice versa, canceling each other out. So we call this destructive interference. So if you just change the distance of those two lasers even a little bit, you will see huge changes to the brightness of the resulting combined light wave.
So effectively, an interferometer works by measuring any changes in the lengths of its two arms.
You can even do this on a tabletop experiment. So when I was an undergrad at the University of Minnesota called St. Cloud State, I built a laser interferometer in the basement of our physics building. And it was sensitive to changes in length of like 100 nanometers or hundreds of nanometers. So really small distances you can test with even simple basement tabletop experiments. Now the state of the art today is not a tabletop experiment. The state of the art in terms of gravitational wave detection are these really enormous laser interferometers, like this experiment called LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. And there are actually two of these things, one in Louisiana and one in Washington State. So these aren't something you can fit in your basement. They have 4-kilometer routes one way before they're reversed and the lasers come back together. And also they send these lasers back and forth hundreds of times before they're recombined. And when all is said and done, LIGO can detect changes in distance as small as like 10 to the minus 19 meters, which is like 10,000 times smaller than the size of a single proton.
It should be said that with this kind of sensitivity comes a lot of background noise in your data. And that's why LIGO has to work really hard to make the experiment as isolated as possible. The two arms of the machines are 4-kilometer long vacuum tubes, and the mirrors they use to bounce the lasers back and forth are suspended to avoid noise from the outside vibrations. All in all, the data extraction done by the LIGO team is definitely impressive.
So it took decades to plan and build LIGO, but it all paid off eventually. In 2015, on September 14th of that year, they observed the first gravitational wave from a merger of two black holes that took place about 1.3 billion light years away. So these were big black holes. One had a mass about 29 times that of the sun, and the other one about 36 times the mass of the sun, more or less. And these two black holes have been slowly in-spiraling towards each other over billions of years. As they got closer, they started to in-spiral faster. And in the last second or even fraction of a second, they spiraled into each other at nearly half the speed of light, forming a big black hole and sending a substantial fraction of their total energy into space in the form of gravitational waves. A few months later, LIGO saw their second event. In this case, there were two black holes again of about 14 and 7 solar masses. And a little over a year after that, a third event of this kind was detected. A couple of years after that, a third gravitational wave detector was added to their constellation of detectors, something called Virgo, which is in Italy. And then, combining this with LIGO allowed them to be more sensitive and to localize the direction that these black holes or these mergers were taking place in. And since then, we've now got a list of about 15 confirmed gravitational wave events. 12 of these are two black holes merging into each other. 2 of them are a pair of neutron stars merging into each other. And one that we're not sure whether it's a pair of black holes or maybe a black hole and a neutron star. It's kind of ambiguous in that particular case.
All of the gravitational waves we've detected so far have been from collisions between huge objects, black holes and neutron stars. And that's because those signals are the easiest to detect. They show up as a significant little peak in the data. But gravitational waves are also made continuously between orbiting black holes and neutron stars. I actually spent a summer doing research on the search for these continuous gravitational waves, and it's tough to see these things through the noise, but it's definitely a possibility for the future. But now let's get back to the moment you've been waiting for, the most recent discovery of gravitational waves.
So on May 21st, 2019, LIGO and Virgo observed another black hole merger, but a totally different kind of event than the ones they'd seen before. This event, which we call GW190521, it's a romantic name, I know, was just announced in September of 2020, so it's a brand new thing for us. And it took place 17 billion light years away. You might think that that would be impossible because the universe is only 13.8 billion years old, and that would be outside of the universe or something like this. But because the universe has been expanding, it was smaller in the past, so this is all consistent with all that. And the merger took place between some really gargantuan black holes with 85 and 66 suns worth of mass, solar masses, respectively. And when they combined together, the thing that was left, we estimate, had a mass of 142 solar masses. Some of the energy, if you're doing the arithmetic, is lost. The two merging black holes don't add up to the mass of the total black hole in the end. This is because a lot of that energy goes into the form of gravitational waves.
So to understand the significance behind this discovery, we have to talk a little bit more about what we know about black holes.
Astrophysicists generally think in terms of 2 kinds of black holes that exist in nature. There are the supermassive black holes that you find in the middle of galaxies. These are millions or billions of times the mass of the sun. And then there are smaller black holes that are formed through stellar evolution. Stellar evolution can produce black holes with masses up to about, say, 50 or so solar masses. Anything bigger than that are unstable, and they get blown apart before they get a chance to make a black hole. So this is weird because the thing that we just observed with LIGO and Virgo involves 2 black holes, not 1, but 2 that are bigger than this kind of maximum mass that you expect from stellar evolution. And this poses a lot of challenges for us to try to understand. Some ideas are that maybe there were smaller black holes that stellar evolution produced, and those already underwent mergers that we just haven't had a chance to see, making these sort of intermediate mass black holes. Or maybe these black holes had a chance to accrete large quantities of matter, basically sucking up matter from some sort of companion over billions of years. That's another possibility. But somehow we wound up with a 142 solar mass black hole. And frankly, we're not exactly sure how that came to be. It's pretty confusing. There's even a small chance, and I think it's small, but it's interesting, that maybe the existence of this black hole is telling us something about the laws of physics. People have proposed a variety of hypotheses or guesses or whatever for ways that other kinds of matter or energy could impact the evolution of black holes, allowing larger black holes to form. These involve ideas like the existence of new, very light particles, or even modifications to general relativity, and some of which involve the existence of extra dimensions of space, things like this. Maybe neutrinos interact in ways that we've never actually observed. These hypotheses would all lead to changes in the way that stars evolve, increasing the maximum possible mass that black holes can be formed with.
When the first gravitational waves were discovered, most of the headlines in news and popular media said something along the lines of, "Turns out Einstein was right again." And that's definitely true. Einstein's theory predicted gravitational waves, and so detecting them is proving Einstein right. But really, proving Einstein right is just the tip of the iceberg of the new possibilities paved by gravitational wave detections. Gravitational wave detectors let us do astronomy in a whole new way, and see things that we could never see before.
Like 100 years ago, all of astronomy was like optical, like just light that your eyes could see. And then, we slowly added infrared and ultraviolet and X-ray and gamma ray and all this stuff to it. Now we're adding neutrinos and cosmic rays, gravitational waves. It makes the old school, optical astronomy seem pretty narrow in comparison.
And the future of the field of gravitational wave astronomy is definitely looking bright.
So in the years and decades ahead, we fully expect that LIGO and Virgo and other gravitational waves detectors will observe a large number of these sorts of events. And maybe not the one exactly like this intermediate mass black hole we're talking about, but probably dozens or even hundreds of different compact mergers. And this will teach us a great deal about how black holes and other compact objects are formed and distributed throughout the universe. It's going to be a very exciting time. Looking farther into the future, we're excited to deploy space-based gravitational wave detectors. In particular, there's a proposal for something called LISA, which we think could maybe be deployed in the 2030s or so. And this would be a gravitational wave detector that's sensitive to much higher frequencies than LIGO or other Earth-based detectors would be. So in particular, LIGO sees ripples in space and time with frequencies in the 50 to 2000 hertz range. This, by coincidence, is about the frequency range that you can hear sound waves with your ear. LISA, in contrast, could detect gravitational waves with like 10 to the minus 4 to 10 to the minus 1 hertz, so much, much higher frequency waves, things that you would never be able to hear in terms of sound with your own ear.
And the reason LISA would be able to reach that kind of sensitivity is because of the huge reduction of background noise that you get when you build your interferometer in space instead of on Earth. You no longer have to worry about cars driving by a few miles away or anything.
So LISA will be not just one spacecraft, but a constellation of at least 3 spacecraft forming a giant equilateral triangle across the solar system. All of these components would be in separate orbits around the sun, and they would effectively act like a laser interferometer with a baseline of millions of kilometers. So whereas LIGO is 4 kilometers from end to end, this would be millions of kilometers across the solar system. So once it's in operation, we expect LISA to be sensitive not only to black holes in the sort of tens of solar mass range that LIGO looks at, but also to supermassive black holes with millions or billions of as much mass as the sun. On top of that, they should be able to detect tens of thousands of mergers between black holes and neutron stars. And it should also detect a kind of smooth background of gravitational waves produced from countless white dwarfs in binary systems throughout the Milky Way and beyond. This sounds incredibly hard to me. It sounds comically hard. It like if you just approached me and said like I've got this idea for this space-based gravitational wave interferometer, and you described it, it just sounds inconceivably hard. But people who know a lot more about deploying things in space and building hyper precise devices and whatever, like they think it can be done, and they have a much more authority to tell you whether this can be done than I can. So just because it seems implausible to me, and all the smart guys think it can be done, so I believe them.
Right. I mean, we were saying before that even the ground-based interferometers sounded impossible.
Yeah, I mean, it's really, I mean, LIGO is really a staggering achievement, and LISA is going to be an achievement on top of a staggering achievement. One of the things I'm the most excited about in terms of space-based gravitational wave detectors is the possibility they could detect a background of gravitational waves that was produced in the early universe. So this is all speculation, but it's possible there may have been uh, really sudden phase transitions or other events in the early universe, maybe associated with the era of inflation, that could have produced a background of gravitational waves that are passing through us every moment of every day. And it's possible that these planned or proposed experiments could detect that background of gravitational waves, teaching us things about our universe when it was a trillionth or a trillionth of a trillionth or a trillionth of a trillionth of a trillionth of a second old, right after the Big Bang. I can't think of anything more exciting than that.
We hope you enjoyed this episode of Why This Universe. We just want to say thank you for all your support. We are so excited to be growing with you. And just remember, if you enjoy the show, please share it with your friends and family and coworkers and kids. And also don't forget to leave us reviews or tweet at us at WhyThisUniverse to let us know what you want to hear from us next. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.